Yes, go ahead.
Okay, yeah, you're not recorded, so. So thank you everyone for attending this event, which is actually kind of special. It's jointly organized by 3 institutes, Trinity College, University of Edinburgh, and Heriot-Watt. So we're experimenting a bit with this, and I'd like to thank both the organizers, Anna and Marcus from Trinity College, and our speaker Justin Vines, for accepting this. So Anna, I'm passing the mic to you to continue with the seminar. Thanks a lot.
Okay, thank you very much. So yeah, we are very happy to have this joint seminar with Edinburgh, and I'd like to thank Justin for agreeing with this seminar to us, and also to proposing this nice idea. So so today Justin will talk about spinning black holes meeting gravitons. So go ahead and thank you.
Great, thank you very much, Anna and Praxiteles, for the invitations, and thanks to everyone for listening. And so yeah, today I would like to tell you about spinning black holes meeting gravitons. Some suggestive pictures here on the title slide, but I'll skip right down to, in case it wasn't clear from the abstract that was sent around, the context for this talk is gravitational wave physics. So LIGO first, 6 years ago, for the first time, saw the first gravitational waves from a binary black hole merger. And since then, there have been roughly order 100 more such events, also some with neutron stars thrown in. Though today in this talk, mostly or exclusively, actually, I'll focus on binary black holes. And in fact, I'm going to kind of focus on the boring part of a binary black hole evolution, let's say, where in the early in-spiral part, let's say the early in-spiral part is the part I'll mostly focus on. Of course, they also merge and ring down. And an important point in gravitational wave physics is that the detectors like LIGO and friends, in order to even detect and especially to characterize gravitational waves from systems like binary black holes, they must have precise templates from predictions of general relativity for what these waves should look like. And these come from 3, let's say, classes, maybe really just 2, but numerical relativity is basically putting Einstein's equations exactly or up to numerical error on a supercomputer, setting up initial conditions that reasonably describe a binary black hole and evolving. And that way you can get the whole thing, maybe not so much in spiral because it's expensive, but from numerical relativity, you can get these guys to merge and ring down. And that's really our best way to go, but it is very expensive and it is also limited in terms of covering the parameter space. So that was here. And then a next also really crucial input is so-called post-Newtonian perturbation theory, where basically if you go in the Newtonian limit, we have the Kepler problem, and then general relativity leads to perturbations away from that as long as you're in the Newtonian regime, which we'll come back to. But in this kind of perturbative approach, you can't access the strong field merger, ring down. And then I also want to mention a really important class, I guess I'll draw it down here, of models that is actually used for gravitational wave data analysis, are these so-called effective one-body models, which somehow put together information from, say, a post-Newtonian in-spiral with, there's also a way to treat the ring down. So not after the merger is done, this ring down can be treated with so-called black hole perturbation theory, solving for, say, linear perturbations off an exact black hole background is also doable, tractable. EOB puts those parts together with some kind of matching at the merger that is very much informed by numerical relativity these days. But the name of the model, these class of models, really comes from the fact that they also have some important strong field information, really the exact test body, they would call it, or for this audience, this might be the better known as the probe limit. If you go all the way in that limit, say it's the motion of a test particle and an exact black hole background, so say Schwarzschild, and that limit is built into effective one-body models, which also combine with post-Newtonian and numerical relativity, and produce, so they're much, you can get an in-spiral ring-down merger waveform from such a scheme, much cheaper than actually doing numerical relativity, and these are very much used in data analysis. Along with, there are also phenomenological models, which are, let's say, more or less directly fitting numerical relativity, although of course with some analytical insights from post-Newtonian. Okay, so for gravitational wave physics, we need precise models. We need to solve the two-body problem in general relativity. This post-Newtonian approach is the most relevant perturbation theory. And of course, the systems that LIGO sees are actually bound systems that in-spiral and merger. So if we're interested in such bound systems, why would we think about scattering? Which is what most of the rest of this talk is going to be about. Well, so one thing to say is scattering is cleaner than bound orbit. Basically because you have simplicity at infinity. You have asymptotically flat spacetime, and you basically have free black holes can be thought of as free particles at infinity coming in and scattering. Things can be much cleaner, and it's easier to articulate like gauge invariant descriptions of the dynamics. Like a nice example is, at least for the dynamics of non-spinning systems, the so-called scattering angle function. So if these two guys scatter in the center of mass frame, let's say focusing on the conservative dynamics, which is also a caveat for in fact, all of the rest of this talk, I'm going to be focusing on the so-called conservative part of the dynamics, leaving out the so-called radiative part. I'll say a bit more about that on the next slide. But if we focus on the conservative part of the dynamics, which in some ways is the more important part, in the center of mass frame, two bodies scatter both by the same angle chi, which can be expressed, say, as a function of the energy and the angular momentum of the system. And that's a gauge invariant function, which actually characterizes all of the information that there is to know about the conservative dynamics. And this is to be contrasted, for example, with effective one-body models, and also post-Newtonian, more generally post-Newtonian descriptions of the motion. They encapsulate usually information that comes from hard calculations in a final result, which is like a canonical Hamiltonian describing the motion. So a Hamiltonian, which is a function of a relative position vector and a relative momentum in the center of mass frame. And that's, of course, though, a gauge dependent quantity, even though that is often considered the best final result of most traditional post-Newtonian calculations. And this is the kind of thing that enters directly in, say, these effective one-body models. And the thing that has built into it that its probe limit describes exactly geodesics in a Schwarzschild spacetime. But it turns out, for example, that the complete information of that function is contained in this function. Even though this is describing scattering, and this guy actually describes both unbound and bound orbits, the complete information of this Hamiltonian is contained in the scattering function. That's something that's been realized in recent years, and is a very good reason to think about scattering, even if you're interested in bound systems. There are many other reasons along those lines. But so let me continue with talking about perturbation theory. So I see a question from Stefan. Why is Hgage dependent? Basically because so this, you can kind of think this is like a position vector. It's like a coordinate or it's like a relative coordinate displacement between your two bodies in your binary. And in general relativity, coordinates are always subject to coordinate freedom or general covariance of general relativity. So in a nutshell, that's why that Hamiltonian is gauge dependent. Or generally, it's subject to canonical transformations, which redefine the position in the momenta. Good question. And please do chime in if you have other questions. So I spoke on the first slide about this post-Newtonian perturbation theory, where basically the limit that we take is the speed of light goes to infinity, basically. And in that limit, you go all the way, you get Newtonian gravity, and perturbations away from that give you post-Newtonian gravity. And so formally 1/c could be our small parameter, but it's truly dimensionless small parameters are this thing, which is basically the gravitational potential gm/r divided by c squared. Or the characteristic velocities of the system squared divided by c squared. And here I put in that these two small parameters in the post-Newtonian regime are of the same order. So this is really an assumption. Together, these define the post-Newtonian regime, but you will also recognize that basically the virial theorem tells us that if we have a bound system, the characteristic kinetic energies are of the order of the characteristic gravitational potential energies. So that's why, essentially, for bound systems, this is true. So most directly for bound systems, we should treat these two small parameters on the same footing. They are of the same order, and that's post-Newtonian perturbation theory. Okay, alternatively, and in recent years, there has been much more interest in this so-called post-Minkowskian perturbation theory, where now the limit that we take is basically to turn off gravity or send Newton's constant to 0. You go all the way in that limit, there is no more gravity, you just have flat space-time of special relativity. Perturbations away from that are characterized by, again, basically the field strength or the potential. But now we let our velocities be possibly relativistic. So, again, that doesn't really apply directly to bound systems. It applies more physically directly to scattering systems. And another thing to say about this is, of course, this would be the natural thing to do for, say, a quantum field theorist or an amplitude person, right? Doing perturbation theory, we expand in the coupling. The coupling basically for gravity is the square root of g, and we would never, in QFT, you would never want to, well, in fact, actually sometimes you might want to, in describing bound states of quarks, for example. You can make this kind of non-relativistic approximation, but more generally, we want to keep special relativity intact and allow arbitrary velocities. So this is one reason why, in particular, in recent years, methods from QFT, in fact, let's just say the scattering amplitudes community, have been able to attack this post-Minkowskian perturbation problem even using quantum methods, methods developed from quantum field theory, but importing them to solve this classical problem, some progress has been made that we'll see a bit more about in the next slide. And finally, a third perturbation scheme that's available to us is to consider the situation where one of the masses is much smaller than the other. If you go all the way in that limit, you get what we talked about before, the probe or the test body limit in a stationary background. And so specifically that limit is, as we also already mentioned, for the non-spinning problem, is geodesics in a Schwarzschild space-time. So that's going all the way in that limit, but we can also perturb away from that limit. So now this guy, we let it produce its own gravitational field, considered as a linear perturbation of the Schwarzschild background, and solve, say, the Reggie-Wheeler equation, which is a name for one of the best equations describing linear perturbations of a Schwarzschild spacetime. That is this so-called black hole perturbation theory that we mentioned. And we can solve the problem then perturbatively in the mass ratio, essentially. But very interestingly, in this case, we can access arbitrary speeds and strong fields. So that's another big advantage there. And so this paradigm for solving the two-body problem in the extreme mass ratio limit, it's often called, goes by the name of the self-force paradigm. And the reason for that is, in a way, the motion of this guy, as it deviates away from geodesic motion, is best described as it feeling a force from its own perturbation to the field, so a self-force. Okay, so those are three distinct perturbation schemes that are available to us to solve the two-body problem, and much of the rest of the talk is going to concern interesting relationships between these three different schemes. Interesting and surprising relationships that have only come to be understood in recent years, really the last 5 years. Okay, so going back first, however, to this post-Newtonian scheme, which is most appropriate for describing an actual binary, here I'm looking at this canonical Hamiltonian that we mentioned earlier. And if I look to the left of this green line now, this part here is just a rest mass contribution, but I hope you would recognize here the kinetic energy and the potential energy for a Hamiltonian describing the Kepler problem. So I'm really describing the two-body problem here with masses M1 and M2, but I made some definitions: the total mass, big M, the reduced mass, mu, and the symmetric mass ratio, nu. And let me go back here and say something. If we look just at the Newtonian limit, we kind of recognize here that with these definitions and with these rescalings, this Newtonian Hamiltonian, which is really describing the two-body system, it's really identical to the Hamiltonian describing the test body limit. When we make this identification that the mass of the effective test body is the reduced mass, and that the mass of the effective background guy is the total mass. So if you will, that is the Newtonian effective one-body equivalence, that the two-body problem is equivalent to a one-body problem at the Newtonian level. Okay, sorry, I was going to say that's the Newtonian part. And then we add relativity, perturb away from that, and we get the first corrections in 1/c², and this is the so-called first post-Newtonian or 1pn level, which, let's see, it usually, the Lagrangian corresponding to this Hamiltonian usually goes by the name of the Einstein-Enfeld-Hoffmann Lagrangian, which they derived in 1934. Actually, it was first derived by Lorentz and Drost in 1917, but nobody knew about it for a long time. And we recognize essentially these things squared divided by the speed of light squared are the kinds of terms that enter at the first post-Newtonian level. These are relativistic corrections, let me just say. And next we have the 1/c to the fourth contributions. That's the so-called second post-Newtonian level. That was, let's say, finalized in the 1990s, just for some history. And nowadays, so let's say, roughly speaking, the next 1/c to the sixth corrections, the so-called 3PN level, were completed in the first decade of this century, and at least the conservative part of the fourth post-Newtonian dynamics was settled early last decade, to give you a sense of the progress here. Okay, but then we also mentioned we can reorganize this expansion in a certain way. Instead of looking at the powers of 1/c, look at the powers of g. So that would be here, the first line is the zeroth post-Minkowskian level. The next line is the first post-Minkowskian level, and so on. And you'll notice, like, each column here, which was a post-Newtonian level, it stops after a finite number of terms, but each row here, which is a post-Minkowskian level, it goes on forever. So when you do post-Minkowskian instead of post-Newtonian, you're resumming an infinite number of contributions in the post-Newtonian expansion. And we also mentioned on the first slide that actually we realized in recent years that the complete information of this Hamiltonian, for example, describing the non-spinning binary problem, its conservative dynamics at least, and this is a gauge dependent thing. I picked some gauge here to write it down, is actually contained in this the scattering angle function, which can be derived from it. And oops. So here I'm calling that chi of B and V. So here back in this picture, chi, remember, was this angle. B is the impact parameter. And essentially V is the relative velocity at infinity, which you could also exchange that. Here I wrote it was a function of the energy and the angular momentum. You can translate between velocity and impact parameter and energy and angular momentum. In fact, I wrote down here the relationship between the velocity and the masses and the total energy in the center of mass frame. That would be, by the way, just what many people here might just call the Mandelstam variable S, is E squared. And I'm claiming up to, so here is the linear in G result to all orders in velocity. Here is the G squared result also to all orders in velocity. This was first derived by a guy called Westphal in 1985, this second post-Minkowskian scattering angle. And I'm claiming that, so up here in this Hamiltonian, all of that information, so everything up to the 2 p.m. level, which, and of course here it looks much more complicated, all of that information is in this very simple function down here. And one last point here is, we mentioned in a sense, the Newtonian level kind of does not depend on the mass ratio, or at least in this way of writing it, it doesn't depend on this symmetric mass ratio, but we see it does come in at 1 p.m. order. And so in the traditional way of looking at this Hamiltonian, we would have said, well, first of all, to get the test body limit, you take this red nu to 0. So if I just drop all the nus here, this is going to be the post-Newtonian expansion of a Hamiltonian describing Schwarzschild geodesics. And it looks like at 1 PN order, there is extra information that is not coming from Schwarzschild geodesics. And similarly here. But when we look at this function, and look at the dependence on the masses, it's surprisingly simple. So apart from this overall factor of the energy, so this guy really doesn't depend on the masses at all. And this guy, the second post-Newtonian contribution, is proportional to the sum of the masses. So a surprisingly simple, besides a surprisingly simple result overall, a surprisingly simple dependence on the masses, which we will come back to shortly. Okay, so I mentioned a lot of recent progress on the post-Minkowskian expansion, even in this non-spinning part. For example, this third post-Minkowskian level was first attacked and successfully so, it turned out, by Zvi Bern and collaborators in January 2019. And that was actually just the conservative part. There has also been a lot of other important work, both before this paper, building up to this paper, and certainly after this paper, further developing it, like also adding the radiative part at 3 p.m., which was, one might say, really only settled final earlier this year. Like, I can throw in a couple of important names. So Thibaut Damour played an important role in solving that, as well as, of course, all of these post-Newtonian calculations. And let me say, Enrico Hermann and collaborators. So Hermann, Par Martinez, Roof, and Zhang were also, well, they really were the ones who finally completed the radiative part of the third post-Minkowskian, and a lot of other work in recent years trying to solve this, the two-body, even just the non-spinning two-body problem in a post-Minkowskian expansion instead of a post-Newtonian. And so let me come back now to this surprising dependence on the masses, which was really only understood after this result came out. So only after this result was out in January 2019, did we have start to begin to have some kind of understanding of what I'm going to explain on this slide, which is the following. So if we consider, so this scattering angle function, the scattering angle function is simply related to, say, the magnitude of the change in momentum or the impulse on the two particles when they scatter each other. It was argued in this paper, again, very much building on these results, that if you really consider simple ideas like the structure of the post-Minkowskian expansion, Poincare symmetry, dimensional analysis, you can come to the conclusion that this impulse function, very closely related to the scattering angle function, must have this structure, which I'm showing here, where, so there's an overall factor of Newton's constant times the product of the masses divided by the impact parameter. And then at the first order, a function which you can't get from just dimensional analysis, but it can only depend on the velocity. And then at g squared order, you get basically g times a mass divided by the impact parameter times a function of velocity, but it must essentially be linear in the two masses. And then that continues. You always add a factor of G times M. So G times M is a linked scale with C equals 1 for the rest of the talk. So GM over B, it's got to be M1 over or M2. So that tells you that this thing has to have this structure really just by dimensional analysis and a couple of other things. But now we add another important ingredient, which is this thing actually has to be symmetric under exchange of the two bodies. So in this non-spinning problem, that's really simple. It tells us that those two functions actually have to be the same. It tells us that those two functions actually have to be the same, and same for those two and those two. So while it looked like we had 1 and then 2 and then 3 and then 4 free functions that we have to determine by actual calculation, it turns out we actually only have 1 and then 1 and then 2 and then 2. And so here I've traded these M1, M2 for, again, that total mass, M1 plus M2, and that symmetric mass ratio. Okay, and now this factor of the energy cropped in here, this really, if you'll believe me, is a kinematical factor that comes in from converting this impulse magnitude to this scattering angle, but it really just comes as an overall factor. It doesn't spoil this scaling with the masses that we were talking about. And then we see some very interesting conclusions. So again, for knowing that that thing had to be there, this function and this function, as well as this function and this function, we are all the same as we would get from the probe limit. So if we look at this expression and take its probe limit, so essentially take nu to 0, apart from this overall factor of the energy, we lose no information at first and second post-Minkowskian order. So 1 and 2 PM, we get from the probe limit completely, even for arbitrary masses. And surprisingly, 3 and 4 PM, we would get from so-called first order self-force, or that is, so these expressions are linear in the mass ratio. So if we could solve the problem to linear order in the mass ratio, so that's what we were talking about here with this black hole perturbation theory or self-force. That's what they do. If we could solve that to linear in the mass ratio, then we would have the complete third and fourth post-Minkowskian results for arbitrary masses. And this pattern continues. So 5 and 6, you would need second order self-force. Okay, and so this was in these terms, and very also pointing out that these black hole perturbation theory or self-force results could be used to inform finite mass ratio post-Minkowskian or post-Newtonian results. That really came for the first time from Thibaut Damour in December of 2019. By the way, all of my references here are the first 4 digits of the archive numbers, so year and month. So that was December 2019. And implementing that kind of scheme, so actually, if you can do these self-force calculations and use them to inform your finite mass ratio post-Minkowskian or post-Newtonian calculations, that process, so self-force to PN, PM, arbitrary masses, that has come to be known as, for some reason, the tutti frutti scheme, because it really combines a lot of different ingredients, so lots of different fruits. But the main ingredients are what I just described. Okay, and I should admit, there is more that I'm not describing, but that has come to be known as tutti frutti. Some people in the audience may have heard of that, and I'm just mentioning here. So besides work, also in the non-spinning case, this kind of analysis also works with spins, and that has been implemented, for example, in this paper by students of ours here at the AEI and postdocs here at the AEI, including myself, to, for example, so without spin, this tutti frutti hasn't been able to fill in something that wasn't already known. But the first example of filling in a new post-Newtonian order that wasn't already known some other way, but using this tutti frutti, tutti frutti is already written there, what was in that paper where we used self-force results to compute for the first time, let me just say, a high order in the post-Newtonian expansion concerning spin effects. Okay, and I could spend a whole hour on that slide alone, but I'm not going to. So more about spin, which is, even though I'm well over halfway through the talk, I really wanted the talk to be mostly about spinning black holes, and I'm just now getting to it. But so here I'm drawing my schematic picture of a two spinning black hole system where, so the masses are M1 and M2, and then I'm drawing this vector A where, sorry, that's not correct. This A vector is related to the spin, basically, and that it's the spin divided by the mass. So remember, so spin, angular momentum should have units when c equals 1 of mass times length. So this A, we like to call the ring radius. It really is, in a real sense, the radius of the ring singularity of the Kerr black hole, which is being depicted here. So that's what this A is. So this is our proxy for the spin. Sometimes people also just call it the spin parameter. And here in the top, I'm showing how, in an amplitudes-based approach to this problem, how, at least through the second order, this mass scaling that we were talking about up here, how that arises, and also how that generalizes, at least to the case of, I definitely should have written this somewhere, aligned spins. So when the black holes are spinning, in general, the spins could point in any direction. And in that case, the motion is not confined to a plane anymore, the orbit of the binary. The orbital plane precesses when the spins are not aligned. But if the spins are aligned with the direction of the orbital angular momentum, then the motion stays in a plane and the spins don't, the spins always point in that same direction. That's a very simple case that is in many ways like the non-spinning case, but richer because the black holes are spinning. Okay, so in that case, well, I mean, a lot of what I'm going to say extends beyond that case, but just for simplicity, we like to focus on that case. Okay, and then up here, what are these amplitudes I'm drawing? Well, the dark lines are black holes, are representing black holes, and the squiggly lines are gravitons. So this is like two black holes exchanging one graviton. That's the tree level process, if you will. And then these are one loop processes, but really here I'm representing unitarity cuts, or let's say in one way of accomplishing this calculation using scattering amplitudes to do the calculation of two black holes scattering off of each other through one loop order. And one loop order corresponds to G squared order, or second post-Minkowskian order. And tree level corresponds to linear NG, 1 p.m. In one way of organizing the calculation, these are the only unitarity cuts that are needed to determine the relevant classical part of the amplitude. And you'll notice, so really that's just this one at tree level, and really it's just the one at the one loop level and its mirror image. And also it's clear from the amplitudes analysis how the mass scaling is going to go. And again, so here I'm writing an expression for the scattering angle again, which is, at least for this aligned spin case, very simply related to the amplitude. I can say in one quick word, the Fourier transform of the amplitude, or maybe the log of the amplitude, gives you a function whose derivative with respect to the impact parameter is the scattering angle. But this mass scaling here, so looking at the dependence on the masses at fixed, so all of these functions, of course, also depend on that velocity and impact parameter that we had before, but also on the spins now, these ring radii. They could be aligned or misaligned. This A's could be positive or negative. But from the amplitudes picture, and one can also argue from classical grounds, we expect this simple dependence on the masses. And so for one of these triangles, there's some function which depends on the two spins. The other triangle is basically that same function, but with the arguments interchanged. So it's a little bit more complicated than the non-spinning case, but the important point is that if we consider the test body limit, so say send one of the masses to 0, oh dear. We are still not going to lose any information. So say take M1 goes to 0. We will lose this guy, but we still have this guy. And that guy has the complete information of the other guy. So we again are seeing that even with spins up through g squared, the complete information of this process is going to be contained in its test body limit. But this is a funny test body limit. So in order to make what I just described work, I have to send one of the masses to 0, but I don't want to send its ring radius to 0 if I want this thing to still depend on the ring radius. So I'm taking the mass of one guy goes to 0 compared to M2, but at finite ring radius. So I really don't have a black hole anymore when I do that. I have a naked ring singularity. Right, so remember, for the Kerr solution, if g times the mass is bigger than the ring radius, that is actually a black hole with a horizon. So I'm depicting the horizons here in black. But if GM is less than A, it's a naked ring singularity. So this thing, which I would like to call a test black hole. So a Kerr-like object of negligible mass, but finite ring radius, is my naked ring singularity test black hole. Now, it's not at all clear that that limit necessarily exists and makes sense, and certainly not to all orders in perturbation theory. But does it exist at this level, at least? Or is there a well-defined limit here at this level, even for starters working perturbatively in the spins, as is often done, as is often necessary to do? So that is still an open question. And so, but okay, so in these pictures that I was showing up here, these diagrams I was mentioning, these are unitarity cuts in one way of approaching this calculation, which I refer you to these papers for more discussion of those technical details. I'm not going to have time for any technical details, but we see the building blocks for these cuts are, so first of all, this 3-point amplitude with black hole comes in, black hole goes out, meet one graviton. So that's here, also that's here and here, these same 3-point amplitudes, if you will. And at one loop, we need this 2 black hole in and black hole out meeting 2 gravitons. So that is the so-called Compton amplitude. It looks just like if these were electrons and photons, that would be Compton scattering. But now I want them to be spinning black holes and gravitons. So that's my so-called black hole graviton Compton amplitude. And I should also say, to do what we were describing above, we just need these amplitudes at tree level. So the tree level 3-point and the tree level Compton describing black holes meeting gravitons would allow us to, well, let's say have allowed us to study the 2 black hole process at tree level or at linear order in G. And let me also just say, at that level, actually, we have a very nice story with many perspectives by now on this story. We can do all orders in that ring radius, let's say, so all orders in spin for these 3-point amplitudes and for this tree level process. There's a beautiful story there, which I was going to tell you some about. Don't know how much time I'll have, but let's just say at this Compton level, well, certainly not yet can we make sense of this to all orders in A. So maybe up to A to the 4th, we have candidate answers of what this black hole graviton Compton amplitude should be. Maybe A to the 5th too, though there's still some work to be done there. And let me just say, there's going to be a correspondence. So that's like from a classical perspective, there's a correspondence with being able to do this in the quantum picture for a massive spin 2 or a massive spin 5 halves particle meeting gravitons. Hope I'll have time to explain a little bit about that correspondence. And if we could understand this so-called Compton amplitude, like I was mentioning above, that encodes, for one thing, how a test black hole responds at second order to a background field. Also tells you how to do the arbitrary mass problem. But another interesting point is that this same Compton amplitude, like if you look at it, so it's a graviton comes in, meets a black hole, and the black hole and the graviton go out. You might wonder, okay, classically, should that not correspond to gravitational waves scattering off of a curved black hole? So could I set up the classical problem of send in a gravitational plane wave to a black hole and see what comes out? And yes, you can set up that problem using linear black hole perturbation theory, which we've already mentioned several times before. And so one idea that some of my collaborators and I have been exploring recently is, can we approach that from a purely classical side and thereby learn about some of these questions about amplitudes on the quantum side? And the thing at the very bottom, I'm gonna just skip for now. Okay, so those are pictures somehow depicting what a black hole looks like. The Kerr shield form of writing the spin, so the Kerr metric for a Kerr black hole can be written in the so-called Kerr shield form, where it's the Minkowski metric plus a null vector field. This is a picture of that null vector field, which has really, maybe just take away from this for now, there's this ring singularity, which is integral to the structure of the Kerr field. And yeah, I'm going to run through the next slides very quickly, but through these series of papers, there was a really nice understanding of, if we restrict to linearized gravity, so of course we understand exact Kerr to some extent, but there's a really nice way to understand a certain linearization of the Kerr metric, which is sufficient for this analysis of tree level processes, or this tree level 3-point amplitude. And there's this really nice way to write in position space the Kerr metric like as a metric perturbation, satisfying the de Donder-Gage condition. And it features this exponential of basically that ring radius times a derivative. Okay, so, and there, I'm afraid in the interest of time, that's all I'm going to say there, except that through a long series of papers with, I mean, so here this is representing at least, let's say this is representing order 15 to 20 papers, through the course of which there has been a very nice story about how that classical description of the Kerr metric that we were just talking about, with this exponential of spin times derivative, translates into a 3-point amplitude, which is also really a simple, it's essentially the 3-point amplitude without spin times e to the momentum of the graviton dotted into the spin vector. Or I should say wave number, momentum divided by h bar. And also here on this slide, I should at least spend a little bit of time mentioning how this story goes back to a paper by Vaidya in 2014, where he noticed that if you look at massive higher spin particles coupled to gravity, and you look at processes, for example, 2 of these things exchanging gravitons, and even he just started at tree level, he noticed that if you take a scalar field and take this, go through a classical limit procedure, you will describe a monopole, a classical point, structureless point particle feeling linearized gravity, let's say. More importantly, if you take a massive spin half or a Dirac particle and couple it to gravity, you add linear in spin, or so-called dipole or spin orbit coupling, which is also universal in gravity. But very interestingly, if you go to spin 1, you get additionally, in a certain way of taking the classical limit, you get classically a quadrupole on that object, which is proportional to its spin squared. So that's typical, oh dear, of spinning objects when they're spinning. So like a black hole is spinning, it becomes oblate. It has a quadrupole moment that's proportional to its spin squared with a certain response coefficient, which you get specifically the black hole value for that response coefficient when these massive scalars are in a certain way minimally coupled. And this pattern continues. Going to higher spins adds more multipole moments. And they continue seemingly, at least at tree level, to match the classical black hole multipole moments when you have a certain definition of minimal coupling. Okay, another interesting part of this story was, so a few years later, Arkani, Hamed, Huang, and Huang had a paper. The title of the paper was Scattering Amplitudes for All Masses and Spins. And they were looking at massive spin S particles meeting gravitons. And the word black hole doesn't appear in the entire paper, but they wrote down certain 3-point amplitudes that they argued were unique minimal coupling. Again, according to a certain definition of minimal coupling, that's essentially uniquely singled out by having a well-behaved, or let me just say a good high energy limit. So again, the word black hole doesn't appear in the whole paper, but they wrote down some amplitudes for massive spin S particles meeting gravitons that are uniquely singled out by having a good high energy limit, a well-behaved high energy limit. And it turns out that, and so I'm not explaining at all, they also introduced in that paper some very convenient massive spinor helicity variables and notation, which I'm using here. It was later realized through the course of lots of different papers that those amplitudes are actually exactly describing a black hole, at least at the tree level 3-point level. And even though this doesn't look anything like this, in the appropriate limit, those amplitudes become what I was describing down here with essentially an exponential of spin. Okay, gonna skip that. So in that same paper, Arkani Hamed et al. Also wrote down some Compton amplitudes. Again, black hole, word black hole, not in the paper, but these are long story short, they bootstrapped these amplitudes from those 3-point amplitudes. It was later shown by these authors that these amplitudes that I'm writing down here are the result of the BCFW procedure applied to those 3-point amplitudes, assuming that there's no contribution from a residue at infinity. Okay. But in the original AHH paper, they just kind of wrote them down and showed that they were consistent with factorization. And just like those 3-point amplitudes, really, this is defined for any spin S. And so there's a lot hidden in these, what's going on with this bold massive spinor helicity notation. But let me just say, this could be evaluated for any spin S, but they knew, of course, it wasn't good for spins. Okay, so actually here, I'm talking about both the photon case and the graviton case. Let me just focus on the graviton case. They knew this could only possibly be good for spins up to 2. And one feature, let me just say, is that when S is 5/2 or bigger, this factor built from the spinors of the graviton momenta and the momentum of one of the massive incoming guys. So anyway, this combination, which is here to the 4th power, it's same thing down here to the, okay, it looks backwards, but it's the same thing to the 2s power. So if S is 5/2, this is in the denominator. And this is a spurious pole, which should not be there. So that's just one feature of why the thing is not good at spins higher than 5/2. In this paper, it was also discussed a good way to translate this into a classical form, which I'm afraid I'm not going to have as much time as I wanted to say anything about that. I see it's already 5 o'clock. So if you'll give me 2 minutes or so, let me just say, this Compton amplitude is not yet well understood. There is a paper by Chiodda-Rolli. I won't write it down. I'll just say Chiodda-Rolli, Johansson, and Picchini from a couple of months ago, looking at, can we fix this thing at least at spin 5/2? And they have an answer. Chiodda-Rolli, Johansson, Picchini. But it's not clear so much yet if we can take a useful classical limit of that answer. But anyway, the rest of the talk was going to be about resolving can we learn more about these Compton amplitudes? Essentially by going to this picture, which I had before, which was, so even on the classical side, we should be able to solve the problem, okay, of if I send in a gravitational plane wave to a black hole, what comes out? And so this is a problem that we have been working on. We put out a paper, not about the actual case we wanted to do, which was gravitational waves scattering off of a plane wave. We put out a paper about scalar waves scattering off of a black hole, solving the so-called Minkowski equation. That's the name for the equation that describes linear perturbations of a Kerr black hole. Okay, and let me just sum up with saying that from our black hole perturbation theory calculations, we've actually, so it was already, if you will, conjectural that, let me say, this amplitude, which is basically the same as the original Arkani Hamed et al. Amplitude, that this is even actually describing a black hole through spin to the fourth, so a to the fourth, if we think about expanding this exponential. That was still conjectural, but so far we have confirmed that actually that exactly matches what we get from the Minkowski equation, and work is in progress to see what the Minkowski equation says about, let's say, spin to the fifth. Okay, and with that, I'll leave this picture up as a summary, and thank you very much for your attention.
So let's thank Justin for the very nice talk. So I don't know if and anybody has questions? Like, feel free to unmute yourself if you would like to ask by Zoom or in the room as well. Like, maybe I can start. So when you start to talk about spinning, you show the table and you had this post-Newtonian and post-Minkowski in very large, like you had like 4 or 5, but when you were talking about non-spinning, you were going into like 4 or 5, saying that now the results are being understood for non-spinning, for kind of so it's somehow like what is understood for this spin for such higher orders in
Okay. So were you talking about this table?
Yes.
Okay. Okay, so what is it? So you could focus, so I wrote both a post-Minkowskian and a post-Newtonian in each block, and it's, if you had that much post-Newton, so for example, here the leading order post-Minkowskian, linear, and spin, if you had that, you would have the leading post-Newtonian order when you re-expand in 1 over c, and that would be so-called 1.5 pn, or like 1 over c cubed. Okay, so first, I think you might be like, what is known in post-Newtonian, for example, and let me restrict attention to conservative dynamics. So I think I can draw a line which is going to separate known from unknown. And well, okay, I'm going to actually leave out the thing that I said that we did for the first time, because that has not been confirmed yet. So I don't consider anything known until it's been confirmed independently. So that the line between unknown and known for post-Newtonian is something like this. If you believe that we can do all orders in spin at the leading post-Newtonian level, which lots of people agree that we can. So that's the post-Newtonian knowledge line for conservative dynamics. I could also draw a post-Minkowskian one. So I'm going to say that 4 p.m. is not done yet, not even for conservative, even though there is some work on it. But I'm going to say that's not done yet. What happened? Okay. And even at linear order in spin, yeah, there is no. So this would be, so for example, for spin orbit or linear in spin, this would be tree, this would be one loop, this would be two loop. Two loop is not done yet. For spin squared, 1 and 2 loop are done. I'm sorry, tree and 1 loop are done. And then for the rest of it, I'm going to say it follows the green line.
Okay, there's a lot to do.
Okay, there
Yeah.
is a lot to do, yes.
Yeah. Okay, thank you.
Yep.
So.
And I made a mistake, actually.
Oh.
No, I didn't. Never mind. Okay.
So we have a question from Donald O'Connor, please.
Right, thanks. Yeah, and Justin, yeah, I mean, you're talking about the scattering function in the conservative case, right? Which is a cool thing. Do you know, is much known about this? You know, if you turn on radiation, right? Just even basic things like, I mean, you know that in the conservative case, the chi gives you all, you know, chi and everything. What about in radiation? I mean, you need chi, and you know, I mean, do we know that you just need chi and say the Newman-Penrose slide 4, or is there more?
Yeah, good question. Well, so yeah, certainly the Newman-Penrose psi 4 would be good for the waveform. But let's say for, like, say, to reconstruct the impulse, say, is the scattering angle enough, including a radiative part of the scattering angle? Is that the kind of?
Yeah, well, I mean, just what's a complete gauge invariant characterization of the quantum state?
Yeah, okay, a complete gauge invariant characterization, right? Okay, but including radiation.
Yeah, I mean, well, my guess, my hope, let's say my hope is that it will be some scattering function at a Newman-Penrose psi 4, but you know, it'd be a good idea to ask you if this is true.
So, I mean, that's a very good question, and I don't know. So, and by scattering function, you mean like something whose derivative gives you the scattering angle? Yeah. Can you include radiation in such a thing?
Yeah, I mean, the thing I have in mind is derivative will give you the correct scattering angle, not some
like the full scattering angle.
The whole thing, yeah, the physics thing, you know, the one that you measure.
Yeah. Yeah, so there certainly exists a physical scattering angle, including radiation, and the radiative part of that. So that's also known, of course, now at the leading part, so 3 p.m. I don't know, just take an antiderivative with respect to B. That's a scattering function which has that in it. Is that the complete information? I would say no.
I don't think it is, right? I think you need to know that and the psi 4.
Yeah, and psi 4, and even just to reconstruct the full impulse, that radiative part of the scattering, or say the complete scattering angle, is not enough. Mm-hmm. So the linear momentum lost to radiation, you would also need to know. So you can't reconstruct the full impulse at 3 p.m. from just the scattering angle, even including the radiative part. There's more information which is in the radiated linear momentum, or the radiated energy.
Hang on, yeah, you mean, yeah, if you just know where it's going, you need to know you don't have everything.
Yeah.
But if you did know where it was going and you had the full, you had the psi 4, then you'd know the amount of energy that was lost, right? So
yeah, so the how much energy is lost, how much angular momentum is, yeah, that's it, encoded in psi 4, certainly.
yeah. So okay, so you could imagine there's a scattering function psi 4 that would do the trick.
Yeah, I could imagine that.
Yeah.
I could imagine that, though I don't know of any. Okay, I should maybe somewhere in some of the papers by Gabriele and Veneziano.
Yeah, I don't know. But yeah, I'm thinking of something a bit like, oh, exactly. Yeah.
Yeah, they have some iconal with radiation.
Yeah, they do. Yeah.
In some sense. But I have to say I'm not very familiar with what's going on there.
Okay. Yeah, thanks. That's great.
Yeah.
So there was a question on the chat as well. It's from Stefan.
Okay.
It says you're looking at C going to infinite and G going to 0 approximation. Is there any useful way to use something like C going to 0 or G going to infinite approximations? So the opposite.
Okay, so G goes to infinity would, I guess, be like a strong coupling instead of weak coupling, or something like that. I don't know off the top of my head. So C goes to 0 seems really weird to me. What would you get in that limit? I don't know. I have never heard of anything like C goes to 0. Really, nor G goes to infinity. But those are intriguing questions. I'm sorry, I don't have more to say than that on those.
Any more questions? Okay. So if not, maybe let's thank Justin again for the very nice talk.
Yes, thanks very much for having me.
Thank you also from here, Justin.
Oh, so
yeah.
actually, can I respond to Stefan? Or Stephanie?
Sure.
Okay, so thank you for reminding. Yeah, C goes to 0 was not making sense in my head, but when you say ultra relativistic limit, that certainly makes sense. So, and yes, that is a very interesting limit. So I would say, let's leave C alone. C equals 1, but essentially, like in this scattering function, for example, in this, what happened? Yeah. In this scattering angle that we were looking at, the ultra-relativistic limit would be V goes to 1. So that's, I'm taking the limit where, yeah, the initial relative velocity is the speed of light. So of course, that kind of implies that one of my particles, at least one of my particles, is becoming massless. And so, yes, that is an extremely interesting limit. You can see here that limit is finite at this level. And it becomes the answer for, so for example, here it's really the same as the test body limit. So instead of describing time-like geodesics in Schwarzschild, it's describing null geodesics in Schwarzschild, or the orbits of a massless probe in Schwarzschild instead of a massive one. Interesting fact, the order G cubed part of this scattering angle function that these guys first derived, it was not finite in that limit. If you took V goes to 1 and their conservative 3 p.m. scattering angle expression, it blew up. It had a logarithmic divergence, which famously, I should say, it goes like arctang of V, which is the rapidity, inverse hyperbolic tangent of this V. And it blew up in the ultra-relativistic limit due to that feature. And in this work, it was, well, really, it was first de Moor who pointed out that it's because that was the conservative part alone, and really what physically only makes sense is the full conservative plus radiative, and if you add the radiative part, it cancels that divergence, and the full complete radiative plus conservative scattering angle at the third order in G is also finite in the ultra-relativistic limit, or the massless limit. So yes, that is a very interesting limit. It's also a very interesting limit when there's spin. Like, even at G squared, when you're trying to, like, it's, should you get a finite limit when V goes to 1 or not? Like, I still don't know of any good reason, physical reason to argue that you should when there are spins, for example. But I could say that if for some reason you knew that there should be a smooth massless or smooth ultra-relativistic limit, that would give you input to help pin down to some extent some of these unknowns at higher orders in spin that I was talking about. Great. Thanks for the question, Stefan.
So maybe let me stop to record.